What's going on, guys? Hope you're doing absolutely amazing. So in this video, we're going to code a neural network from scratch. To really understand the theory behind neural networks, you need some math, and I've made all the derivations for what we're implementing today in a blog post, as well as 3 previous videos going through all the theory. So if you want to learn more about that, check out those videos. So in this video, we're just going to focus on the implementation, and I will bring up the relevant parts as we go through it. So you might be able to follow even if you haven't had those, especially if you have some math background. But so what we're going to do is we're going to import NumPy as NMP, and then we're going to do from utils import create dataset and plot contour. So these are just 2 help functions I've created here. They're on my GitHub if you want to read through them, but it's really just to generate some data to make it nice to look at. And then we're going to do class neural network, and we're going to have an init. We're just going to send in x and y, so our data set. Let me just also write the other functions that we're going to have just to sort of have a skeleton code. We're going to have one function to initialize weights. Particularly, we're going to use Chi-Ming initialization, which takes sort of the nodes in the previous layer and then the nodes in the next layer. So a special type of initialization. You can also just do some normally distributed weights, but this one has been proven to work better. Then we're going to do a for prop. We're going to send in x and parameters, and all this is going to make sense as we actually write this part, but just for the skeleton code. Then we're going to do compute cost, and we're going to do y probs and parameters. Then we're going to do a backprop, and for the backprop we're going to send in a cache, parameters, and y. So I'm not expecting you to know why we send in those. It's going to make sense. We're going to use them. And the last thing we're going to do is we're going to do update parameters. So this is going to be, a gradient descent step. And then we're going to have a main function that takes in those x and y, and then we're going to do it for some number of iterations, let's say 10,000. Okay, that's going to call all of these functions right here. So initialize weight, and we're going to have forward propagation, of course, and then we're going to compute the cost. So that's sort of the end of the forward prop, but we do it in a separate function. And then we're going to have backprop, gradient descent step, and then a main function that's going to call all of those functions. And yeah, we're also going to have, so we're going to run neural network from here. And so we're going to do x and y, create data set. Let's say we have 300 points and classes, 3 classes, for example. So that's just the util function that I created previously. All right, so let's start with the init function. We take as input x and y. So we're going to do x.shape. And xShape is the structure of the data. For this to work is to have the training examples. So we're going to use m for the amount of training examples as the amount of rows that we have, and then self.n are the number of features. Okay, so m training examples, n features. Then we're going to do self.lambd. So that's for the regularization part. And then we're going to use self.learning rate, and we're just going to set this to 0.1. And then we're going to define size of neural network. And so what we're going to implement here is a 3-layered neural network, and that's also what the derivations I've done in the blog post is based on. I might do a sort of an entirely generalized neural network in the future. Let me know if you'd be interested to see how that looks like. So you would kind of just say what nodes you want and how many layers, and it would automatically do it for you. Anyways, we're going to use, in the first hidden layer, we're going to use 25 nodes. And then in the last one, so the last one is going to be the number of classes that we have, right? one way to do that is we can use the length of np.unique of y. So this will kind of check how many unique values are input. So yeah, you can check out how that works. Really nothing complicated. And then yeah, so we're gonna do chiming initialization, and so w will be np.random.randn, and it's gonna be, let's see, the shape is gonna be L0 L1. So that's the amount of nodes it's coming from, and then the amount of nodes it's going to in the next layer. So the previous layer and then the next layer. And then we're going to do times np.square root of 2 divided by L0. So that's just chiming how it's defined. And then we're going to use b to be np zeros of L1 comma L1. Then we're just going to return those. And then let's see, we're going to go to the for prop. And so parameters here is going to be a cache, a dictionary. And we're going to store all the necessary weights and biases in those parameters. So what we're going to do is we're going to do w is parameters of w2. w1 will be parameters w1, and then b2 will be, yeah, sort of the same, but b1, b2 instead, and then b1 like this. So how we're using w1 here is it's going to take, that's the one that goes, so the weights are, w1 are the weights that goes from the input layer to hidden layer 1, okay? w2 will take sort of the input from layer 1 to layer 2, okay? So the 2 here is representing the layer that it's going to. Yeah, so we're gonna do for prop. We're gonna initialize a0 to be x, just to make it sort of nice. We're gonna use sed1 to be np.a0 and then w1 plus b1. Okay, that's just the linear part. And then we're gonna use a1 is gonna be the relu applied, so np.maximum of 0 comma z1. And then z2 will be np dot of a1 and w2 plus b2. So sort of note here why we wrote a0 here, because it's the exact same form as we do here. We just increase one layer, right? So this is the input layer, this is the result from the first layer, and this is the result from the second layer. And since second hidden layer rather, sorry. So it's a total of 3 layers. And then what we're going to do is we're going to do, as last, we're going to use softmax, because we're now on the last layer, the output layer. So we're going to use scores is z2. Then we're going to use softmax, which is, we're going to do x of scores. And then we're going to do finally probs is going to be x scores divided by np sum of x scores comma x is 1. And then we're going to do keep dims equals true. So we're just, so what we're doing here is we're taking the x of all of the scores. So remember, we have the final one will be sort of the let's see, we're going to have scores to be the number of training examples that we send in, perhaps in a batch, or if we just send in the entire training data. And then it's going to be comma the number of classes, so num classes. So this will be the shape. And so we're taking the exponent e raised to each element wise of the number of classes. And then what we're doing here, we're just normalizing so that we can say that each node is sort of representing the probability that it's that particular class. Essentially, the sum of all of the classes will be 1. And then in the end, so we're not done with the for prop, and we're gonna store some things that we're gonna use in the back prop. So we're gonna do a0 is x. We're gonna do probs is probs, and then a1 is just A1. Then we're going to return cache and props. All right, fair enough. The next thing we're going to do is we're going to compute the cost. And first thing we're going to do, we're just going to take W2 from parameters of W2, W1 parameters of W1. And then we're going to sort of compute the loss in two parts. We're going to have a regularization part and a sort of the loss from the actual data. So we're going to have data loss, which is going to be np sum of minus np log of prop. So this is cross entropy loss, if you're familiar with that. And then we're going to do np.arrange self.m comma y. And so we're only taking the log of so all of the training examples, but we're only taking the log of the one that is supposed to be the correct class. And that's how cross entropy is defined. Then we're going to do divide by self.m, and that's the data loss. So we're going to then use the regularization loss, which is going to be 0.5 times the regularization parameter self.lambda. Then we're going to use np.sum of w1 times w1, and then plus 0.5 times self.lambda times np-sum of w2 of w2. And then the total cost will then be the data loss plus the regularization loss, and we're just going to return the total cost. All right, now perhaps for the most, so I guess the hardest part, I'm just going to copy in these. So we're just going to unpack our parameters, and then I'm going to copy this as well. We're just going to unpack from the forward prop. So there are some computation that we're going to need when doing the backprop from the forward propagation, and we're just going to take them out from the cache that we send in here. Then what we're going to do, so we're going to start with calling dz2, which is the cost with respect to z2. I'm just writing it here for more compact notation. We're going to set this to probs. So remember, we're now starting at sort of the end that we computed during the for prop, right? That's what we computed as our last step in the forward. In the backward, we're just starting from that, and we're going one step at a time backwards until we get to W1, W2, and then B1, B2. And so what we want from this is we want, so DZ2, DW1, DW2, DB1, DB2. Those are the parameters that impact our model's predictions, right? So what we're going to do then is doing the derivations, as I've done in the other videos and in my blog post. It's gonna end up pretty nice, but the gradient, the loss with respect to the probs or dz2 is gonna be minus equal to 1 for the specific for all training examples, but only minus 1 if for the correct node, for the correct class. And then we're going to divide everything by self.m. And then we want to, now when we've computed those, we can backprop to dw2 and db2. I can show sort of a graph of how this looks like, where we're currently at, and in the graph. And now we want dw2, which is going to be np dot of a1 transpose, the one that we brought from the cache, and dz2, and then we're gonna plus self.lambda times w2. Yeah, so that's just dw2. db2 will be the np sum of dz2, x is equals 0, and then keep dims equals true. Now that we've done that, we're gonna go to the next, so the in this case the only hidden layer. We're gonna dz1. So you can sort of view it as a graph, and we're just moving one step at a time backwards. We're going to do np dot of dz2 w dot transpose. Again, all these derivations are in my blog, and I'm going to show them as well as to perhaps make it more clear. Then we're going to do z1 times a1 greater than 0. So this is just the rel, right? If it's greater than 0, it's going to be 1. So this is just going to be 1 or 0. And then we're ready to backprop to dw1, which is going to be pretty much exact like this one. So we can copy that one. We're going to change it to 1, and we're going to change this to 0, and then we'll change this to 1, and then 1. And the b1 is going to be sort of the same as this one, except we're going to have dz1 here. All right, so now we computed all of the gradients, right? We want all of those, and that's exactly what we have now. And then we have grads, so we have dw1 to be dw1, dw2 to be dw2, db1, db1, db2, db2. And so what we want to return are the grads. Awesome. So this is the hardest part of the entire neural network. So what we're going to do now in the update parameters, this is going to be, I guess, pretty easy. We're just gonna I'm gonna copy this in. We're gonna get all of the parameters, and we're gonna get all of the gradients. And remember, gradient step, the gradient step is just gonna be w2 minus equals learning rate. So I guess self.learning rate times w2, and same thing for w1 and w1, and then also similarly for b2 and b1. Right, so those are sort of the now updated values of those, and we're gonna store all of those in parameters in a dictionary, and we're gonna do, let's see, w2 b1 b2 b2, and then return parameters. Right, so now we've done sort of all of the functions that lead up to the actual main function. And what we're going to do here, first of all, we need to define, run the initialization. So w1 b1 is self.init timing weight. I guess that's what we call it, right? Init timing weights, yeah. And we're going to send in the first, so that's the number of features. Right, for w1 is going to take the input layer to the first hidden layer, and it's going to take, so the input layer is self.n, and then the next one is self.h1, and then w2 and b2 will be the same thing right here, except we're now going to send in self.h1 to self.h2, right? H2 in this case is the number of classes. That's the output layer. We're going to pack everything, so let's bring this down so it's more centered. We're gonna have parameters now, and we're gonna send in everything to this one. Let's see, b1 b1 b2 b2. Great. So now when we have all of that, we're gonna do for iteration in range of num iter, and then let's do +1, just for a nice plot, since it doesn't anyways, so we're gonna run it for a specific number of iterations, in this case 10,000. I guess since we added 1, it's gonna run 10,001, but since we're gonna plot the cost sometimes, it's gonna be nice if we just have that +1 right there. It's not important though. And then we're gonna do the forward prop, and so this is kind of forward prop. So this should be easy now, right? We've already made the functions. So we all need to do just cache props is the output from the forward prop, and we're going to send in x and the parameters. Then we're going to calculate cost, and the cost will just be self.compute cost, and it needs y, probs, and parameters. Then sometimes, so if iteration is 2500, we're going to print at iteration, we have a loss of cost. And then after computing cost, we're going to do the backprop. So the gradients are self.backprop of cache parameters and y. And then we're going to update parameters. So parameters is going to be self.update parameters of parameters and grads. And that's sort of it, right? At the end of the main function, we perhaps want to return parameters. And yeah, so hopefully there are no errors now. Let's first of all, let's run this first. And we're going to do, let's see, the plot. Okay, maybe it's already. So right here. So yeah, this is how the data looks like. So it's 3 classes. And now what we're going to do is first we're going to do y is y as type int. It's just, I can show you it. I think it's needed for, let's see, this part right here. When we're indexing right like this in a matrix, this needs to be integer and not float. So that's why we're doing as type int here. Then we're going to do nn is neural network. We're just going to initialize our class. We're going to send in x and y. Then we're going to do train parameters is nn.main of x and y. And x and y. And then we're going to call plot contour of x, y, and we're going to send nn. And this is not really important. This is just for the nice plot. So what this is going to do is going to show the decision boundary that we obtain. But let's run this first. So we can see right here, see at iteration 0, 2500, we sort of see the loss is decreasing right here. And if we look at the plot now, we can see that this is the final decision boundary that we obtain, which looks pretty nice. And we can see that, okay, it sort of makes sense what it's doing. It's finding the pattern in the data. So that was a really, really, I guess, quick walkthrough of how to code a neural network. Hopefully it was clear. If you have any questions, leave them in the comment and I'll do my best to answer them. Neural networks are hard, and that's why I've done 3 previous videos and a separate blog post just for the theory of this. Thanks for watching the video and hope to see you in the next one.